Hi, today I want to talk about the user interface for Fishkibble. This is the third part of the breakdown. What you're looking at now is the skill tree. It's a skill tree with a progression system. There are a lot of skills and things like that. I just want to focus on the UI. Then there's the skill main level where you can see your various attributes and level them up as you progress. And there's the player HUD, which is pretty basic. There's a crosshair. You can see a compass there at the top, which I'm going to focus on today. And there's the HUD at the bottom left, which shows some of your attributes. And the UI has various animations. There's the checkpoint animation that just played on the UI, so you can just indicate it that you saved the checkpoint. There's also the conversation system, so you can interact with other characters, and as you do that, various topics will pop up. And then there's also the journal where you can see any of your active quests, current objectives, completed objectives. At the moment I'm not in a quest. And there's completed quests where you can see, and you can also view past discussions or any interactions that you had with characters. And these are all done with Unreal Engine's Unreal Motion graphics. You can take a look at some of that now. Let's quickly start a quest. So I'm talking to this guy. And then once you've started a quest, it'll start coming up in your active quest UI. So I want to focus on the compass. So once you have a waypoint, you'll see a little green arrow starting to pop up. We're waiting for an enemy fish to spawn. There we go. So you can see there's a green arrow on top of the AI fish or the enemy, and there's one in the compass. So north is the world's x-axis, which is right. Then there's east, west, and then south. And the waypoint will move along. If the waypoint's moving, it will show on the compass. The waypoint will always be visible even if it's behind you, so that you know you have an active waypoint. And you can see it's working pretty well. Oh, he's coming for me. So let's quickly see how some of that stuff's done. Like I said, this uses UMG. Unreal Motion graphics. So looking at the player HUD, there's a lot of things happening here, but the way that they've done animation on the user interface is, and that's basically properties that change over time. So you'll see here's a timeline, and there's a lot of animations in this user interface. You can animate various properties. So I'm just gonna, let's look at the screen tint, for example. I'll just quickly show you what it looks like. You've already seen it, but let's just quickly do it again. This won't save check. Well, this won't reload because it's the test level doesn't load from the saved game. So the minute the AI detects me, the screen's going to flash yellow. There we go. So you saw the yellow flash. And that's done using obviously just images. This is an overlay image. This is the HUD itself, and it references this image here, which is called UI Screen Fill. And if we just open up that texture, you'll see it's just plain texture with some opacity. And here's the screen tint animation, and you can actually slide this, so you can see that's the animation that would play. And how it's done, it's actually, if you look at the opacity track here, you will see these values interpolating as it's getting closer to the keys, and there are, I think, 3 keys set. the first one is 0, the second one 0.7, and the last one 0 again, and then it will reset back to 0. That's an example of the alert overlay. There are a lot of animations. Obviously I'm not going to go through them all. I just want to focus on the compass stuff at the moment, but you can see there's a lot of stuff that can be animated, and the things that you can animate is really, there's a lot. You can do transformations, which are translation, rotation, scale. You can also animate image properties, like I'm doing here. You can animate the colors, the opacity, and various things. So let's take a look at the compass. And see how that, well, what I just quickly want to show you is how the screen tint animation is actually fired, which is also important. When the game starts up, and this character is the main character, we go to the event play function, begin play. There's a lot of stuff happening here, but what I want to focus on is create player widget function. This gets called throughout the course of the begin play function, so it'll only get called once, and it's only getting called for the main character, not for any AI. It also does a lot of stuff, but what it's most importantly, it creates this player HUD. It creates that widget and puts it in this property called HUD reference, so that we have a reference to it from our character. And then what would happen, for example, if an enemy detects us, it's going to call this broadcast prey function to tell that it found an enemy, and you are the enemy obviously for an AI, and it's going to call this hunting party started event. Now this is a blueprint event, and if you go and just quickly look at that blueprint event on the character, it calls this blueprint function being hunted function. And what this does is it calls this alert screen tint function, blueprint function, and it will get a call the screen tint animation on that HUD reference. That HUD reference is just a widget which then gets cast, and then this is an animation, the screen tint animation. This is a get function of the player HUD, so we're getting a reference to this animation here called screen tint, and then it's just calling play animation on it with some properties. So it's literally calling play animation when you're being hunted. So that's the mechanics of how the animation interacts from the character to the HUD, but there's also things that happen from the HUD to the character. For example, the compass does some interesting things. So the breakdown of the compass. It consists of a background, which is a plain image, a texture. This is sort of the theme of my UI. I'm going to close some stuff we don't need to see. Alright, and then it has the compass texture. Now the compass texture is a little bit special. It references this, it uses, they call it brushes. In real epic games call these brushes. It's, which I guess you would brush stroke. I don't know the significance, but it's a texture, and this references the compass inst texture, right? This is a material instance. Material instance is a basically derived from a parent instance, and allows you to have, it obviously does a lot more than that, and it's specifically for graphics optimizations and things like that, which we don't need to delve into for this. But yeah, it's really a lot more optimal to use instances of materials than the materials themselves everywhere. because of the way draw calls and rendering and the way that it's handled internally. I mean, you guys can read up on that. So this guy references derives from a material called compass material. Now, a compass material has it's a little bit of a funky one. The material domain has to be user interface for it to be used or be able to use in the UMG, and it exposes this vector or color called pan. So this is a parameter, so it can be changed. It can be changed at runtime if you just need to do a few special things, which we'll go through. I just want to show you how this material works, how the compass actually works. So the UI itself does not animate the compass. The texture isn't animated. The texture is moving because it's being driven by material functions. So the pan parameter is passed in and changed, and this is obviously done every time it's rendered. This shader will run because that's what a material is. It's a graphic shader that runs as part of the pipeline. So for materials we don't need three, or even we don't use the alpha. We don't need red, green and blue, which we're actually only interested in 2 because it's X and Y, because it's 2-dimensional. So we only take the first 2, which is red and green, and we create a new vector, 2D vector from that, X and Y. So those 2 values are simply extracted out, and a simple add function. This texture coordinate function is useful if your compass texture needs to tile or tile differently, or even if you have multiple textures in there, you can specify the coordinate index if you have multiple coordinates, because you can have tiling, tiled or column and column and row type textures, which like texture atlases. You can use them, things like that. But there are better ways than using texture coordinate for that. So then that's that value is simply added to its UVs, and the value that we'll be passing in is actually only going to be, I think it's only the x-axis. We're not going to move up and down, we're only going to move left and right, and then that's goes into the final color, and the opacity obviously comes from the image and is unchanged. So how does it know where to move it to? Is a good question. And let's just quickly finish the breakdown. We'll show you how that's done. So there's a compass overlay, which is not important at all. Then there's the compass waypoint, which is also an instance material, and if we open that up, it's a simple little arrow, and it derives from exactly the same material parent, which is compass material, which is this guy. So the material, the texture itself, is also exposed as a parameter and can be changed, which is why it's visible here and overridden. And for the compass material itself, for the instance, it's not overridden because it's using the default. And you'll see the pan parameter is also, none of these values are set at design time. This is all going to be changed at runtime, meaning when the game starts. So now we know we've got a compass that can move. So the texture itself can move around in this little panel here. The panel itself isn't moving at all. So the panel is static and the image inside of it is moving, and the image itself is tiled. So it wraps. So if the end of the image is here and it moves to the middle, the beginning of the image is going to be visible there just before it. So it will look seamless, because the texture has to be seamless when you create it. Like I said, the overlay isn't important, that's not animated. So when the game runs, the compass tells you which direction you're pointing in, and it follows the waypoint, and the waypoint itself can move around. So how is that done? Looking at the user interface, the Unreal Motion of the UMG UMG objects or widgets, that's a better name for it, widget, also has an event graph, and we're using that. Well, I'm using that. It has tick event, and it has event construct. So event construct is run when the widget is constructed. So before you can make any changes to a material during gameplay, because there's a difference between having a material and having a dynamic material, which is a little bit more, you take a bit of a performance hit if you want to do this, but it's worth it on the current hardware we have. This isn't I've seen some worse things in AAA games that are shocking. So and this is the way that you do it. It's optimized as best they could, because I mean it's taking values from the CPU and writing them to the GPU on a very frequent basis. So there's almost no getting around that, because it has to change frequently, where materials normally don't have to change, so they can stay on the GPU as long as they're being used. And that's where the most expensive part of it comes in, is copying the memory over from one to the other, and the parameters. I mean, these parameters itself are small, but the shaders themselves affect that data. So anyway, what you do is you create a dynamic material. So first of all, we determine, is the compass material valid if it's set? Because if you're going to try and create a dynamic material instance on something that's not set, it will crash, fall over, or give you funny errors. You know, I always check for nulls, or check for stuff that's not there. It's very important. Everybody should do that. So then we call this create dynamic material instance. This is an Unreal function. You pass it in the parent material that you want. In our case, it's compass inst, and we simply set the result of that operation or function. So creating a dynamic material instance from the compass instanced material. Now that's a freaking mouthful. And we set that in a variable called compass material, which is of type material instance, right? And then we override the brush from the UMG image compass. The UMG image compass is this guy right here. UMG image compass. It's this blue guy. Well, not blue, it's the compass itself, the text that we saw just now, the panning image, this. Right, so we're overriding this guy now with a dynamic material instance. And then it does the same. If a waypoint material is set, which is the arrow, we create a dynamic material instance from the waypoint instance, set it in the waypoint material variable of type material instance, and override that by calling setBrush from material, passing in the UMG image waypoint. UMG image waypoint is the arrow. Right, so now the game has started, the widget was created. Now we have two dynamic material instances, meaning we can change the pan property at runtime, or doing whenever we want, basically, and as frequently as we want, because it's optimized as best they could to do this. The compass itself, if you look at the tick event, so it also has a tick event. In other words, every frame this function is going to run, and it calls this adjust compass function. The adjust compass function is what's actually changing the compass. We simply get a handle to the player character. This could be cached, but these operations themselves are really not that expensive. Then we use this variable called CurrentWorldDirection from the player character. Now this CurrentWorldDirection has a friend called CurrentWorldDirectionWayPoint. And before we carry on here, I want to show you where that comes from, because that's important. So if you look at the blueprint character itself, the current world direction waypoint are properties, and these properties come from the C++ character, the Fishkibble UE4 character. Current world direction waypoint and current world direction. So they're exposed in C++ and completely editable and readable in Blueprint. They fall under the interaction category. So if we were to scroll to the interaction category, they would be there. They should be in here somewhere. There they are. Okay, how are they calculated? We go to the tick event of the character. How did you just jump away? And we go right to the bottom. A lot of stuff happening here. The code that's running here will only run for the main character. It's not going to run for AI, because it uses this check, which we went through in the previous breakdown, how this variable is set. So the calculate world direction to waypoint function is called every tick. Don't actually need the delta seconds in this function, but I did pass it anyway. I usually do to indicate that this is called every tick. So we need to calculate the current world direction as a heading between 0 and 360, meaning which way are we facing in the world. Where 0, I think 0 is north down the positive x-axis, which is, just click on something, the positive x-axis is there, facing that way. You can see the red arrow there, so that's positive x, that should be north. Well, that's how I made it. Doesn't have to be, but that's how I made it. So these calculations work according on that. So the way we do it is we get the rotation from the follow camera. The follow camera is simply the camera that's following the character. All characters have this, even AI, because AI are possessible, so they also have cameras. They're not active, so if they're not active, they're not taking up space or resources. So we use the rotation from the camera, the yaw. We get the rotation from the camera and we use the yaw. So the yaw is the rotation around the up axis, which is actually around the z axis, running in circles. 0 is east. That's interesting. Plus north minus south. Okay, well I chose 0 to be north. And then we need to do a little bit of just a little bit of thinking, because the value that I need is not going to be between 0 and 360. The value that I need for this to work, if we go back to the compass, and its parent, I won't close them again now, you can just stay here. The value that we're adding here, we're adding to UVs. So if we're going to add 360, or a value between 0 or minus 300, negative 360 to 360, this thing is going to go all over the place because they're not related to each other. So we need a value we need a value between 0 and 1. So what I'm doing here is I'm just using a simple min-max normalize function, passing it a minimum and a maximum value of 0 and 360, and saying if the depending on where the world direction, what the world direction value is between 0 and 360, bring me a value back between 0 and 1. So this is a simple min-max normalize function. It's pretty standard, it doesn't do anything special, so it gives you a parametric value for a value between a min and a max, and it will clamp, so it will not go over. If it's in this case, it will never be less than 0 because we're doing that check, but if it were, it would return 0 and not some weird negative value. it's important that we get the sign right here, because we want the compass to not jump when you're rotating around. So if I, this time I'm not going to close it. Yeah, well, we can see the compass. So I'm just spinning around and just looking at the compass. You can see it. It's not jumping around anywhere as it's reaching the end or the beginning of the texture. You know, with scaling, it's interpolating between 0 and 1, and you can see it's smooth. Same for the waypoint. The waypoint will also not jump around. So that's why the sign is important. If it's positive or equal to 0, we want the value of between 0 and 1 to be positive, and if it's negative, we actually want the value between 0 and 1 to be negative, but we also have to use negative 360, because if you pass in a negative value and you ask it to min-max normalize to a positive value, it will return 0 and it won't work. So that's the world direction. Simple. It's really simple to get that value. We'll go through how it gets populated now in a second. If we do have a current waypoint, this comes from the Quest system, which I'm not going to go through today. We'll go through that next time, or maybe the conversation system. Haven't made up my mind. Excuse me. If we do have a current waypoint set, we need to calculate the current world direction to the waypoint. Now that's obviously different than calculating the waypoint that we're facing, because we're facing north, and our waypoint might not be north. Our waypoint might be behind us or somewhere else, so we need some way to calculate the waypoint relative to us, and that's very important. Relative to us, not relative to the world. So the first thing we do is we get the look at rotation. This is just simply this is just actually creating a direction rotation. So it's rotating I think it's a quaternion. No, they use F rotator, isn't it? Yeah, they use F rotator, so they don't use quaternions. I'm not sure what the underlying implementation is. This is an Unreal Engine specific rotation mechanism, I think. It might be based on quaternions, I'm not sure. I'm not always up to date with all that stuff, but it's not a matrix. They use their own thing. They might have some underlying, obviously have some underlying matrices. So we're finding the look at rotation, which is a nice descriptive function, from the follow camera to the active quest, current objective, waypoint. This will be set because this function will not return true if that is not set. That's how this is built. So it will always have a waypoint if the current waypoint is set. So we're finding the look at rotation from the camera to the current waypoint. So from us, wherever the character is, and it's important that it's from the camera, because the compass is from the camera's perspective and not from the character. That's an important point to make. I'm going to close this one more time. If you look at the camera, it's rotating. The character is still, which is the desired behavior. I want to be able to orbit around the character. But the compass must move, because I'm not facing, the camera isn't facing, what's this, south. So the camera isn't facing south, no, it's facing north. So the compass must move with the camera, not with the character. If you were to change that function to use the character, it would find look at rotation. It would use the yaw of the character and not the camera. Then it would use the character's rotation, and the compass wouldn't move. It will only move once you start moving the character, which would be very confusing. So the next step then, after finding the look at rotation, so now we have an F rotator that basically looks at the waypoint from the camera, and now we just take the camera's yaw and subtract the yaw we just rotated from that, well, just created from that, and that in itself we can't just use yet. If it's less than negative 180 or less than equal to, could have used, I guess. This is to do with the tearing or the jumping, so that it doesn't jump when it reaches 180 degrees, which we don't need to do here. And then we do the same function that we had here. So this I could have probably refactored into its own method, but that's fine. So if it's positive, it creates a value, parametric value between 0 and 1, wherever it lies between 0 and 360. So if this value is 360, it will return 1. If it's 0, it will return 0. And then we do the same if it's negative. We return the negative value between 0 and minus 360. Even though it probably will never get to minus 360. Interesting. And that's how we do that. So now we have that value. But we still don't know how that value is used. But it's fairly easy. So in the tick event of the player HUD, we're back to adjust compass. We got a handle to the player character. That's how we got this current world direction. So we get the current world direction from the player character. This is happening every tick, and that's calculated every tick. As far as synchronization goes, I think the C++ tick runs first and then the blueprint tick, just out of interest. It doesn't matter if this tick runs before the character tick or the character tick runs before this tick. It's irrelevant, and it should be. The design should always be interoperable and decoupled. So now we're simply setting a vector parameter value on this compass material. So this compass material is the dynamic material instance we created in the event construct. So we're calling set pan. The parameter name is pan, which is just going to jump back to the UMG compass again, if I could see it. And then I'm not going to close it again. Parent. So it derives from this, and the parameter we expose there is a vector parameter called pan. So it sets that parameter, and this itself is just a float value. Obviously, it's a float value between 0 and 1, and we need the pan parameter to be a vector. So I'm simply just calling here make linear color, where RGB and A is not used. We're only using X, which is red, R. And then we need to do the same. So now we've set the pan parameter on the compass, and the compass is going to start, the texture is going to start moving around as we're moving, and it's not smoothed, it's not linear, it is immediate. So there's no smoothing and all of that. The compass doesn't act like a real compass. If you spin around, it slowly interpolates toward there. I want it to be immediate because that's more useful. It's not about fanciness, it's about usefulness for me. Then if there's a current waypoint set, then we need to do exactly the same thing for the waypoint material. So then we simply set the pan parameter on the waypoint material from the current world direction to waypoint. And this is just toggling some visibility if it needs to be shown or not, because the waypoint can disappear and reappear based on various factors, how close and how far it is. And that is how the compass works. Don't think I left anything out. Yeah, awesome. Thank you.